The three-phase circuits is the next topic that we are going to start looking at. And in the three-phase circuits, basically, first of all, we should answer the question as to why three-phase. Why did we adopt three-phase? That's the first question we'll have to answer. Otherwise, there is no point in really talking about simply, why we are generating three-phase, why we are distributing three-phase and all that. So three-phase basically is three different voltages. We are going to have three different voltages which are phase shifted from each other by 120 degrees. Okay. So we are going to have these three voltages which are phase shifted from each other by 120 degrees. So what happens in this particular case is, let's say I have VA, VB and VC. Generally we mention them as ABC, or sometimes we mention them with three colors: red, yellow and blue. So we say RYB. So we call this as red and yellow and blue. Generally, if you look at the wiring in many places, it will go with this color code. So the three phases are always wired with red color, yellow color and blue color. And the ground wire is generally green. Okay. And if there is a neutral, sometimes there will be a black, because neutral and ground could be different in some places. So the neutral will be black and the ground will be green. That is the way normally it is all wired. So what you are going to have is three voltages, and three voltages what we are looking at. If let us say one of the voltage is somewhat like this, let me draw with red. So if one of the voltage is somewhat like this is the sinusoidal voltage. Please note, I'm going to divide this into 60 degrees interval. So this is the 60 degree interval I'm dividing it into. So this is first 60 degree, this is the next 60 degree, this is the following 60 degree. So at 120 degrees, I'm going to have the second voltage starting. Okay. So I should, yellow I'm not able to see, doesn't matter. Let me draw with green. So I'm going to have the second voltage going like this. And it should have the same amplitude. I cannot have lower amplitude. So I should have the same amplitude as that of red. So this is the way it is going to be. And the third one, what I'm talking about as blue, that will again start from the 120 degree point of the second voltage. So I'm going to have the third voltage starting like this and going like this. So this is the way the three phase voltages are going to be. This is R, this is Y, and this is going to be B. These are the three voltages that are going to be generated independently. But when we have three phase voltages generated independently, very clearly, there will be three phase currents as well. So if I'm going to have a resistive load, for example, I will have probably the current exactly in phase with the voltage. So I'm going to have something like this for R phase current. If I'm talking about R phase current, this is how it will be. So if I am looking at the power will be oscillating in every phase because all of them are sinusoidal in nature. So I'm not going to have a constant power. But when I add three phase powers, because all of them are oscillating, the sum of all of them will be a constant in three phase case. So this brilliant discovery was made by Tesla initially. So he said that if you have multi-phase voltages and multi-phase currents, the total power what you get will be a constant. So one of the major advantages of multi-phase transmission, particularly three-phase transmission, I am going to have sum of the three-phase powers is going to be a constant, a fair, I mean, even if there is a little bit of harmonic content, maybe it is slightly far away from sinusoidal waveform, even then you will have fairly constant value of power. So this is going to be a constant. This is one of the major advantages we are going to have. And why do we need this power to be a constant? If we are talking about a three-phase motor, if we are generating a constant power, in that case, we are going to have the torque also as a constant. Torque multiplied by speed is a constant, but inertia is generally large. The speed cannot fluctuate much, so the torque will become like a constant. So the vibrations in the shaft and everything is decreased quite a bit. Whereas single phase motors will always have oscillatory power. If I am talking about a single phase motor which is having a voltage like this, and let us say the current is slightly lagging behind. So let us say this is the current. So it is going to start from here, and the positive half cycle is something like this, and the negative half cycle is something like this. So this is the way the current is, let us say. So this is current and this is voltage. And when we look at the product of the voltage and current, which we call as the instantaneous power, the instantaneous power will be negative during this portion because your current is negative and voltage is positive. So I'm going to have a power somewhat like this, and from here to here the power will be positive. So I'm going to have the power going around like this. So this is the way the power will be. Please note that the power is continuously oscillating. It's not going to remain a constant. Whereas if I look at three phase, if I have three such powers superposed on each other, but they are time shifted depending upon how the voltage is and how the current is. So we are going to have sum of, let's say, power in A phase plus power in B phase plus power in C phase generally will be a constant. If it is a constant, we are not going to have too much of vibrations because you are not going to have the torque and speed continuously changing quite a bit. So torque and speed in a motor, especially if we are talking about a motor, we want them to be fairly constant to avoid vibration. So that is the reason why three phase was initially adopted. It is going to show as though the power as well as torque almost remains as a constant. If I try to look at what is the variation of power and torque with respect to time, it is going to be a constant. Whereas in single phase case, so this is the three phase case, only in three phase case. Whereas in single phase case, this is the way the power changes. So this is the kind of variation you are going to have in the power. The second important thing about three phase is that the advantage of three phase is that, let us say VI cos phi is the power of one single phase. Okay, so in this particular case, I'm going to have one conductor carrying the current. So this is the forward conductor, and I may have multiple loads connected here. Imagine this is a transmission line. So I may have multiple loads connected here. Each load I can think of as a home, maybe to which I'm supplying electricity. There has to be a return path. So I have to have a return path. So I'm going to have a forward path and a return path. So if I look at the entire length and breadth of India, you can say about 2000 kilometers one way and 2000 kilometers again from north to south and east to west. So the transmission lines have to go through the entire distance of the country, which means I have to have one forward and one return path all over the country. Okay, and I will be able to transmit a power of P. Okay, so I should say two transmission lines literally, okay, of length L, let us say each, okay, length L, and you are going to have 2L length transmitting a power of P, for example. On the other hand, if I'm going to have three phase, normally we have three phase, three wire system or three phase, four wire system. What I mean is I would be able to transmit again 3 times P, which is three phase power, only with 3 wires or with 4 wires. Okay, how we are going to do it? We'll look at this right now when we are looking at the three phase systems on the whole. So we are going to have just with 3L length or 4L length of the wire, we would be able to transmit 3P. which is the total power, 3p watts. Here we are only transmitting p watts. So with 2L length, 2L meters of length, we are transmitting only p watts, whereas we are not using 6L, but we are using only 3L or 4L, but we are able to essentially transmit 3 times the original power that we transmitted in single phase. So you save a large amount of copper. So these are the major 2 reasons why 3-phase is very, very commonly used, right? We could have gone for 4-phase, we could have gone for 5-phase. It would have actually allowed us to save more copper, no doubt. But only thing is, within the machine, even accommodating 3-phase is not very easy. You have to segregate those circuits. They cannot have any short circuit. So you imagine that, let's say I'm going to have my machine like this. So I have to probably have A-phase conductors here and A-phase return conductors here. Then I might have to have B-phase, C-phase conductors, return conductors here, and again C-phase return conductors here. Then I might have to have B-phase here and B-phase here too. So I can call this as A, maybe A dash. I can call this as B, this as B dash, and I can call this as C and C dash. This is the way the conductors are distributed. You can imagine as though the conductor is going into the board. It is going like this. It will turn around and the return will actually come through this. So I have to show it as though it is turning around from here and the return is coming through this. And this is turning around like this and the return is coming through this. So if I call this as C1, C2, C3 and C4, I have to call this as C1 dash, C2 dash, C3 dash and C4 dash, for example. Okay, so when I look at 3 phases, the 3 circuits have to be segregated clearly within the machine. The more the number of phases, it's going to be more complex in terms of segregating them. It's not going to be very easy. That's the reason why we have limited ourselves to 3-phase. So very commonly used phase system is 3-phase everywhere. You might see sometimes 2-phase, you might see sometimes 4-phase and 5-phase, but those are very rare. That's not common at all. That is the way it is normally. Okay. So this is basically the importance or the significance of 3-phase system. The 2 major portions are, one is you will save on the copper for the same amount of power being transmitted, and the second one is there is no oscillatory torque or oscillatory speed. So the vibrations in the shafts are decreased. So generally, as a rule, any motor which is greater than about 5 kilowatt to 10 kilowatt, that will be 3-phase motor. You will never have an AC motor which is of 15 kilowatt or 20 kilowatt or 800 kilowatt as single phase motor. Always larger power rated motors will be 3-phase. It will never be single phase. So let's now start with how do we generate 3-phase. You are going to use only one conductor for A phase, one conductor for B phase, one conductor for C phase. Sometimes the return conductor, which is the neutral. So inclusive of that, there will be 4 conductors. Sometimes you may use only A, B and C. You will not even use a return conductor because whatever goes through A will return through B or C. Whatever goes through B will return through A or B and so on. That is the reason. Okay. We will look at the connection of 3-phase. That will make things clearer. We are not talking about the length being smaller. We are talking about the number of conductors that you use being lesser. In single phase, you have to use a forward and return path. Whereas in 3-phase, you might actually have the freedom of using one of the phase conductors as the forward path and the other one as the return path. It is possible. Okay. So we look at it how the connections are made. So how do we generate 3-phase electricity? We had already seen how to generate single phase electricity, if you may recall. So we are going to have, let us say, one conductor like this, which is actually connected to the load ultimately. This is single phase case. Okay. So on one side, you're going to have the North Pole, and on the other side, you're going to have the South Pole. This is what we said. Okay. And this particular conductor, I can show as though if I just look at the cross section alone, I can show as though these are the two ends of the conductor, two sides of the conductor. Okay. So let me call this as A and maybe this as A dash, which is the return. Okay. The same way I can arrange the conductor in such a way that, let's say this is my North Pole and this is my South Pole here in the machine. And I'm going to arrange one conductor here, which is say R and R dash. Okay. I'm going to arrange one more set of conductors, which are going to be arranged exactly 120 degrees away. This is 180 degrees away. So 120 is somewhere here. So I'm going to have here maybe the next phase of conductors. I should not show it as though it is very much outside. I should show it right here inside the cylinder. So let me show it as though this is here. And I'm going to have another set which is sitting here. So I can have in this circular rotor or something, if I'm going to have this as the rotating part of the machine, okay, and this is the stationary part of my electrical machine. The stationary part is generally known as stator, okay, and the rotating part is normally known as rotor. So the rotor portion will be attached to the shaft of my steam turbine or hydro turbine or one of those things in the generating station. So this set of conductor R and R dash first face the north and south pole. Then after it rotates by complete 120 degrees, you are going to see that these two conductors face the North Pole and South Pole respectively. So I'm going to have, let us say I call this as Y and Y dash. And I'm going to call this as B and B dash. So I'm going to have first R facing the North Pole and South Pole, and it is going to have generation of electricity. Then I'm going to have Y and Y dash facing the North Pole and South Pole. Then I'm going to have the B and B dash facing the North Pole and South Pole. Please note they are arranged in space 120 degree apart from each other. Okay, but time wise the electricity generated will be essentially apart 120 degrees apart from each other, because each of these conductors face the corresponding poles after 120 degrees of elapsing time, omega t. If I try to look at it, that will be 120 degrees. So I am going to get the three-phase electricity like what I showed earlier. So I'm going to have one of the phases actually having the sinusoid like this, and I should show it as though these are shifted from 120 degrees from each other. So the second phase will be somewhat like this, and the third phase is going to be somewhat like this. So these are the three phases that we are showing is we are just having the conductor going like this, and it is going to come out like this, and then it is going to return like this. It is returning through this. Now where I have got this brought out, here I can connect an independent load if I want to. Okay, the same way I can do it for B, the same way I can do it for C. Please note that all these three windings are independent of each other. They are all completely insulated from each other. They are also insulated from the core because it has to be inserted into the core, which is actually the outer periphery of the rotor. The rotor is going to actually have stampings again. You are going to have something like this as the rotor structure. So you can imagine as though this is the kind of teeth that is protruding in the rotor. And I have to show it. Let me show it completely. It doesn't matter. It is taking some time. And I'm essentially having this like this. So I'm going to have the conductors inserted inside the slots like this. Okay. So I can have for two slots, I can have R phase, another two slots I can have Y phase, another two slots I can have B phase, and so on. That is the way I'm going to arrange it. So I have three-phase conductors like this, Now I can imagine as though I have one R phase here, then I'm going to have Y phase here, and I have to show as though B phase is coming up here. So this is R, this is R dash, this is Y, this is Y dash, and this is B, and this is B dash, and I should be able to connect simply loads across this. I can have independent loads across this. I'm showing the loads as resistances. It need not be, but I can have it like this. Instead of this, I can connect them together. How we will connect it together? That is essentially either in star format or in delta format. Okay. So in star format, what I will do is, if this is R and R dash, and this is Y and Y dash, and I'm going to have B and B dash. Okay. So R dash, Y dash, and B dash I'll connect together. Okay. And what I will do is I'll take this out, I'll take this out, and I'll take this out, and I can connect resistances also in star format. Why this is viable, we'll look at it in a minute, but this is one way of connecting it, where I can use the neutral, this neutral and this neutral I can choose to connect if I feel like, but it doesn't matter. So this is essentially three wires what I'm trying to transmit. This wire, and this wire I'll use as transmission line. Or another way of connecting is, if I'm going to have R phase here and Y phase here and B phase here, and if I say this is R, R dash, Y, Y dash, and B, B dash, I can connect Y dash to B, R dash to Y, and finally B dash to R. I'm connecting them together. Why this is also viable, we'll talk about it. But I'm going to take one, line out here, one more line out here, and one more line out here. So three lines will do the job in this particular case. This we call as delta because we are essentially connecting it like this. We are connecting them together. So we call this as delta. Whereas here what we have done is, we have one phase here, one phase here, and one phase here. We have just put them together and then we are trying to take this out. So this is generally known as star or Y, whereas this is known as delta. We said that the advantages of having a three-phase AC supply is that one is we are going to have a steady torque, steady power. Both will be steady. Steady torque and steady power will be generated in an AC motor if we supply it with three-phase supply. Okay. This is one of the major advantages, which means we are not going to have any vibrations, not continuous oscillations in the speed. So no vibrations, no oscillations in the speed. So this is what is generally needed in many of the industries which are using electric motors. For example, if it's a textile industry, you don't want color threads which are coming for weaving. You don't want that to come in a very irregular way. So the same way, if it is a tire making industry, if it is having threads, then you don't want the threads to be completely irregular. All those things will be possible only if there are not much oscillations in the speed and you are able to control the speed quite well. The second thing we said was to transport a power, a single phase power of P. If I need, let us say, V meters of wire, copper wire. Okay, so this is actually forward and return conductor together. We should be able to do this with, let us say, V meters of wire. So if we are transporting 3P, that is 3-phase power, we are not going to really use, right, 3 times V. Rather than that, we would only use, if we say V by 2 multiplied by 3, or at the most V by 2 multiplied by 4. That is going to be the length of the wire that you are going to use when you are using a 3-phase transmission. So you save a huge amount of copper. If you imagine like the complete grid that is all over India, from north to south and east to west, it is like about 2,200 kilometers. So you can imagine the amount of copper that is being spent in terms of transmission lines, and that can be really saved when you use this kind of 3-phase transmission. So these are the major 2 reasons why 3-phase transmission is generally used, and 3-phase is utilized even for motors. And 3-phase giving steady torque without any vibration, this was a brilliant discovery by Tesla. Tesla is the one initially who invented 3-phase induction motor, and then it was really popularized by all the industries eventually because 3-phase transmission took over completely. That is the reason. Okay, so the generation of 3-phase. We talked about this already. I'm just reiterating this. How the 3-phase generation takes place. If you try to look at it, if I say that this is going to be the stator that I'm going to have. So let us say I am having an armature or the stator in a 3-phase generator somewhat like this, and imagine that this machine is extending into the board. Okay, so I'm going to have 1-phase conductors somewhat like this. So one is, I'm going to show dot as the current which is actually coming out, and cross as the current which is going in. So this is cross and this is dot. So let me call this as A, and let me call this as A dash. The second set of conductors, let me say this is B, and this is going to be B dash. Okay, so let me call this as B and this as B dash, and let me call this as C, and let me call this as C dash. So I'm going to have 3-phase conductors somewhat like this, and we are going to rotate probably a magnet. So let's say this is North Pole and this is South Pole, and it is attached to a shaft, and then this is going to be rotated, in which case A phase will generate electricity, then B phase, then C phase, depending upon in which direction I am rotating. If I am rotating this in clockwise direction, first A phase conductors will face North Pole, then B phase, then C phase. So that is the reason why we are going to get 3 independent supplies. So I can show A phase somewhat like this. Okay, and I'm going to have B phase. So this again I am showing with respect to omega t. Okay, so this is going to be 0, this will be pi, and this is 2 pi. And this is one complete cycle. So this is one cycle from here to here. So I am going to have this as the first voltage waveform that is coming between A and A dash. And I'm going to get a second voltage waveform which is going to be 120 degree shifted, because spatially they are shifted from each other by 120 degrees. So I'm going to have this as B phase waveform, and the third one which is coming up here, this is going to be the C phase waveform. So this is C phase waveform. So I'm going to have these 3-phase waveforms coming up somewhat like this, and I can connect independently loads across each of these. So if I assume that A and A dash windings are like this, and then B and B dash windings are like this, it need not be only one conductor. Obviously it will be a bouquet of conductor, and then I'm going to have C and C dash somewhat like this. So let me say this is A, this is A dash, this is B, this is going to be B dash, and this is going to be C, and this is C dash. Okay. Now each of them can be represented by, for example, the voltage generated here, if I am representing as Vm sine omega t, this will be Vm sine omega t minus 120 degrees or minus 2 pi by 3 in terms of radians if I write. And this will be Vm sine omega t plus 2 pi by 3 or minus 4 pi by 3. Both of them will be one and the same. Right? So these are the three voltages that are generated. And if I want to connect independently some loads, I can definitely connect loads across these two and these two and these two, although they are all connected. They are all generating the electricity within one generator or one machine itself. So I should be able to connect the resistance here, and I should be able to connect the resistance here, for example, and I should be able to connect the resistance here. In which case, I will need totally 1, 2, 3, 4, 5 and 6 conductors. 6 conductors will be needed to transmit this electricity. So if I don't connect them at all, if I use them as independent circuits, I am going to require 6 independent wires to transmit electricity, one for the forward path, the other one for the return path in every phase. This is how it is going to be. Okay. Rather than that, can I connect it in some way that I would be able to utilize this electricity without having 6 wires? So let us say I have the same conductors here. This is A dash. This is going to be B dash. And this is going to be C dash. I can definitely connect these two together. I can definitely connect these two together because they are independent circuits. It's not a major issue. So let me call this as VA. Let me call this as VB. And let me call this as VC. So I'm going to have VA here, VB here, and VC here. Please note what I have done. I have connected B dash, which is the end of B phase, to the beginning of A phase. And I have connected the end of C phase to the beginning of B phase. So end and beginnings I have connected together. Now what I can check is whether I would be able to connect this to this portion. That is the end of A, whether it can be connected to the beginning of C. If I have to do that, these two should be at the same potential. If they are not at the same potential, I cannot simply connect the two. Then there will be a huge heavy circulating current and there will be huge sparking. So let me try to look at Vm sine omega t, which is Va, and this is VB and VC. So let me try to get what is VA plus VB plus VC. That will be the voltage across whatever is VC A dash. Between C and A dash, if I try to look at it, this will be the voltage. So this will be Vm sine omega t plus Vm sine omega t minus 120 degrees and Vm sine omega t plus 120 degrees. This is what I'll get as the overall voltage. So let's try to calculate this. This will be Vm sine omega t, and this is sine of A minus B and sine of A plus B. So sine of A minus B plus sine of A plus B will be 2 cos sine, cos A sine B. So, right? So we are going to have this as, we can write Vm sine of 2 sine cos. I'm going to get first of all 2 sine of 120 and cos of omega t. So I'm going to get this as to sine of 120 degrees and cos of omega t. This is what I'm going to get, right? Am I correct? So in which case you would have sine of 120 is how much? Sine of 120 is 180 minus 60, which is going to be root 3 by 2. Okay. So, or even if I add them vectorially, I can show it this way also. Actually, if I am going to write this as Vm sine omega t, which is Va, Vb will be 120 degrees away and Vc will be another 120 degrees away like this. So this is Vc, this is Va, this is Vb, which I am mentioning as phasors right now. So VA and VB, if I try to add, first of all, I had to show it as though this is like this, right? So I will get a vector exactly which is opposite. So this is going to be equal and opposite to that of VC. So we'll have to just check whether we get the same thing here also. So this is going to be root 3 by 2. So you will get root 3 Vm cos omega t. Have I written sine and cos somewhat differently? You have to check. So this is cos omega t root 3 Vm. So these two should have gotten cancelled. I might have made a mistake, but vectorially you can very well see that Va plus Vb is exactly equal and opposite to that of Vc. So Va plus Vb plus Vc is going to be equal to 0. Okay, so in which case, if this comes out to be 0 ultimately, so if this is coming out to be 0, that means between this point C and this point A dash, I'm going to have literally 0 voltage. So I should be able to connect them together. So I can connect this point to this point directly. I should be able to connect this point to this point directly. So if I am connecting them together, now I can take out the output from here. I can take out another output from here and I can take out another output from here. So I may call this as line 1, which is going to give me some output. Then I can connect this line 2 and line 3. Now I can connect again 3 resistances, maybe in delta, that should not be a problem. So I can connect one resistance like this, one resistance like this, and third resistance like this. And I can connect line 1 here, line 2 here, and line 3 here. Okay. So this particular connection where you are connecting the end to beginning and end to beginning and so on, this is generally known as mesh or delta connection. So we call this as mesh or delta connection. So in a simplified manner, we can show it as though we are having 3 windings connected like a triangle. And I can call this point as, for example, A and A dash, and I can call this point as B and this point as B dash, and I can call this point as C and this point as C dash. Okay, and now from here I can connect the 3 resistances at the output. So this is delta connection or mesh connection. Okay, and this is possible only because Va plus Vb plus Vc is equal to 0. At every instant of time, this is going to be true. Okay, so this is delta connection or mesh connection. There is one more type of connection which we can have, in which case again let me show the 3-phase windings here. So these are the 3-phase windings, and let's say I am going to connect all the beginning points together, that is A, B and C. All 3 of them I'm going to connect together. So I'm going to connect it like this. and I'm going to connect that to here. So I have connected A, B and C together. Now from here, let us say I connect one resistance here. I'm going to connect another resistance here and I'm going to connect the third resistance here. I can connect these also together. Okay. So if I look at it, I'm going to have VA here. I'm going to have VB here and I'm going to have VC here and I'm going to have some current IA flowing like this. Okay, and I'm going to have another current IB flowing like this and I'm going to have another current IC flowing like this, and I'm calling this star point or this short circuit of all the three phase beginnings, I'm going to call this as the neutral point. So this is the neutral point or star point. Okay, so this is, let us say, capital N, neutral point. Now I have to see what is the current that is going to come out from here. If I may call this as the load's neutral, small n. This is the neutral point of the load. What is the kind of current that is going to come out of here? So I have to look at what is IA plus IB plus IC. That will be equal to IN according to Kirchhoff's current law. So if I try to add these things, this is again very similar to what we got as VA plus VB plus VC. After all, if it is a resistive load, the currents will also be exactly at 120 degrees phase shift from each other. So this will come out to be 0 provided IA and IB and IC are exactly balanced. What we mean by balanced? Three-phase balanced current. Three-phase balanced currents talk about two things. One is magnitudes or RMS values, peak magnitudes or RMS values should be the same. This is the first thing. The second thing is the phase shift between each other has to be 120 degrees exactly. So these two conditions are adhered to. We call this as balanced currents. So if I'm going to have balanced currents, then it doesn't matter whether I connect this to here or not. This capital N and small n can be connected to each other. That is not really going to carry any current at all, because if IA plus IB plus IC equal to 0, whether I connect this or do not connect this, it's not going to matter. This point is going to have the same potential as that of this point. The current is 0, that indicates that I have these two potentials to be exactly one and the same. Okay, so that is the reason why I can have star connection also possible with the fourth wire. I call this as the fourth wire. So I can have one wire, this is the second wire, and this is going to be a third wire. So I can have three-phase, three-wire star connected system or three-phase, four-wire star connected system. So this is essentially Y or star connection. Okay, star or Y connection. This is called star or Y connection. And in star or Y connection, you are going to have basically the junction point of all the three phases. I can indicate like this. This is one, this is the second, and this is going to be the third. I can say this is A dash, this is B dash, and this is C dash. And this point in the middle, I can call this as capital N, which is the neutral point. And I can again have the resistances connected in star or delta. It doesn't matter. From here, I can connect it to this. And from here, I can connect it to this. And the third one can be connected here. Okay. Now this point I'm calling as small n. These two, if you want, you can connect. Otherwise, it doesn't matter if you don't connect as well, especially when I'm having balanced condition, balanced current condition. I don't have to connect these two at all. So it can be three-phase, three-wire, star connected system, or I can have three-phase, four-wire where the neutral wire will also be there. Then I call this as three-phase, four-wire star connected system. So these two are essentially two different types of, star connected system itself. In certain cases, we will see the neutral. In certain cases, we will not see the neutral. Particularly, if we are looking at our domestic supply, whatever we have as our domestic supply, most of them are going to be single phase supply. And when we talk about single phase supply, we will generally supply it between the neutral point and one of the phases. So this happens to be a single phase supply. So whenever we look at a substation which is close to domestic locations, we will have four-wire system closer to our domestic location, and in four-wire system, invariably the domestic supply will be between the neutral and one phase. So this is normally the case, especially in domestic distribution system, wherever we are going to talk about distribution going to houses, electricity distribution which are going to houses, those are going to have generally neutral connection also coming out of the substation. Now, if I look at the star connected system, okay, I talked about basically three wires connected somewhat like this, or three windings of my generator connected somewhat like this. So we said this is A dash, B dash, and C dash. Okay. Now whatever is the winding voltage, we called that as VA. We called this winding voltage as VB, and we called this winding voltage as VC, and these are the three lines that will be taken to the transmission system. Now if I look at the three lines here, what is the voltage between these two lines? This is generally known as the line voltage. We call this as line voltage. And whatever is across one winding, we call that as the phase voltage. For example, if I am trying to look at what is the voltage of line B, A with respect to line B, we call that as VAB. Similarly, line B with respect to line C, we call that as VBC. Similarly, line C with respect to line A, if I try to calculate what is the voltage, we call this as VCA. So we would call VA or VAN, if I may say VAN, because this is neutral. So VAN, VBN and VCN, or simply I can say VA, VB and VC. These are phase voltages. Whereas if I try to look at what is VAB, VBC or VCA, that is voltage of A with respect to B. So I can write this as VAN minus VBN or VA minus VB. Similarly, I can say VBN minus VCN, and I can say VCN minus VAN. These are called line voltages. These are line voltages. So I'm going to have phase voltages and line voltages. Let me try to get the relationship between these two. So if I am looking at, let us say, Vm sine omega t minus Vm sine omega t minus 120. This is going to be VAB. So if I try to do this, I should first of all draw the vector diagram also, because I want to show both the vector diagram as well as the calculation. So if I say this is going to be VA and this is going to be VB. Okay. So this is VA and this is going to be VB. So if I try to take what, and this is VC, let me put VC also, doesn't matter. So this is going to be VC. Okay. Now if I want VA minus VB, first of all, I have to take this VB to the other side. So this happens to be minus VB. So I have to add VA and minus VB. So I'll be able to get what is VAB. So this is going to be VAB. This is VAB. Okay. So VAB, you will get that as root 3 times. If you try to look at it, this is VA and this is VB. So if I say that Vm sine omega t is the peak, Vm is the peak value, Vm divided by root 2 is going to be the RMS value per phase. If I try to calculate what is the RMS value per phase, it will be Vm by root 2. So let us say this I am drawing in terms of RMS magnitude. So this is going to be Vm divided by root 2. This will also be Vm divided by root 2. Please note this will be 30 degree and this will also be 30 degrees. Okay, each of them will be 30 degrees because this is 120. If I try to draw VB, this will be 180 degrees. So this entire thing will be 180 degrees. So because of which you can say you are going to have basically between this and this entire thing is 180. This is 60. Clearly this will be 60, right? And from that I can say this is half of that and this is half of that. So that will be 30 degrees each. So I can write this VAB as VA multiplied by cos of 30 plus VB multiplied by whatever is the magnitude multiplied by cos of 30. So cos 30 is root 3 by 2. So I am going to get this to be root 3 multiplied by VA or root 3 multiplied by VB. So what I'm getting is that this is the line voltage. Line voltage will be equal to root 3 times phase voltage. Magnitude wise, if I try to look at it, line voltage will always be root 3 times phase voltage. So whenever we look at the transmission line, what we see, they will all be carrying line voltages. So if I try to look at this, the transmission lines, what are ultimately coming out of the generating station or what you see as three-phase transmission line, which are hoisted on the transmission tower, they will always be carrying line voltages. Whereas if I try to look at the voltage between neutral and whatever is the voltage here, this will be phase voltage. Each of them will be phase voltage. So if you normally see at home, our single phase power supply at home is somewhere between 230 to 220 to 240 volts. Okay, whereas what is transmitted from the substation generally will be V line, which will be root 3 times this V phase magnitude. So root 3 times 230, if you say roughly, it will be 400 volts, roughly. So that is the reason why Normally you would see many of the motors, three-phase motors will be rated for 400 volts, but at home whatever appliances we use, they will all be rated only for 230 volts. So the three-phase appliances, what we see normally always mention the line RMS voltage. They are going to mention line RMS voltage, but single phase appliances normally will specify phase RMS voltage. Many of them will be specifying only phase RMS voltage. Okay. If I try to look at delta on the other hand, so we looked at star and we got a relationship between the line voltage and phase voltage. They happen to be different in star because the winding voltage is the phase voltage, whereas between two adjacent lines, whatever we have as the voltage, that is going to be your line voltage. Whereas if I look at delta, let me show this as the delta connection. So I'm going to have one connection like this, second connection like this, and the third connection like this. And I'm going to take out three lines. This is one line, this is the second line, and this is the third line. Okay. So in this particular case, I am going to have, let us say, this as A and this as A dash, and this is VA. So if I try to look at what is the voltage difference between this point and this point completely, that is exactly the same thing what is appearing across this winding. So this will be VA. Same as phase voltage. And same way, if I say this is going to be B and this is going to be B dash, and I call this as VB. So I am going to have this voltage, what is coming up across these two will be VB. Okay. The same way, if I assume that I'm going to have this voltage as VC, which is actually between C and C dash. This is VC. So I am going to have this as VC. So we got this as VA, which is same as that of the phase voltage across winding corresponding to A phase. This is the same as phase voltage which is existing across the winding corresponding to B phase, and this is corresponding to winding across C phase. So these are going to be the three phase voltages which are VA, VB, VC. And in this particular case, if I may call this as line 1 and this as line 2 and this as line 3. Between the lines, whatever I'm getting as the voltage is same as phase voltage. So this is the case with delta connection. In delta connection, the winding voltages which are incidentally phase voltages, those will be equal to line voltages. So I would say in delta connection, V phase equal to V line. But if I want to really extract any appliance which is rated for 230 volts, I will not be able to connect it here. There is no neutral point. No neutral point available in delta connection. So generally towards the fag end of distribution, where you are going to connect your domestic appliances, you will have to have only star connection. So towards the fag end of distribution line, where domestic supply, domestic or homes have to be supplied. Homes have to be supplied with electricity. We will need a neutral point, So the connection has to be star. The three-phase connection has to be star because you need to have the neutral point available. Otherwise, you are not going to be able to supply 230 volts. Only line voltage will be available. But look at the current though. If I am going to have a current which is IA in this direction and IB in this direction, this current in I line 1 will be equal to IA minus IB. Okay, so the same argument holds good. If I am going to have, let us say, IA like this, IB like this, and IC like this. These are the three-phase currents. IA minus IB was I line. So let me take this IB to the other side. So this is minus IB. And IA minus IB was I line 1 according to what we wrote here. So I line 1 was IA minus IB. Right? That's what we wrote. So if I try to get what is the value, it will be very, very similar to what we got for the voltage in the case of star connection. So if I try to look at what is IA minus IB, this is going to be root 3 times either IA magnitude or root 3 times IB magnitude. So I'm going to have either root 3 times IA or root 3 times IB, or I can say in delta connection, I line is going to be equal to root 3 times I phase. In fact, I can write in capital because I'm talking about RMS values. RMS values normally we indicate in capital. Okay, instantaneous values, when I write IA equal to IM sine omega t, then we try to write that in small lowercase letter, small ia. If I write capital IA, generally this is talking about RMS value. Very often that is how it is indicated. So I line will be equal to root 3 times I phase in delta connection. But voltages are one and the same if I try to look at phase and line. On the other hand, if I look at star connection, if I say that IA is flowing here, the same thing flows here as well, in the line as well. So this is going to be same as IA. So between the line and the phase winding, which is generating the voltage, the currents are no different. So I can say I phase equal to, rather capital I can write. So I can write I phase equal to I line in the case of star. So just to reiterate, I would say in star connection, I am going to have V phase multiplied by root 3 equal to V line. And I'm going to have I phase equal to I line. Whereas in delta connection, I am going to have V phase equal to V line. Whereas root 3 times I phase equal to I line. Okay, so this is the way you are going to have the voltages and currents related in star connection and delta connection when they are supplied by three-phase balanced voltages. Okay, now what is the power that we talk about in three-phase? So we said that if I'm going to have, let us say, three-phase star connected supply, for example, and I'm going to connect, let us say, one resistance, second resistance, and third resistance. It need not be resistance. In fact, I can have the three-phase load to be RL load for that matter. So I can have one R and L, another R and L, and the third R and L, for example. So I can have three loads. All the three loads, if I may call this as Z, this will also be Z, and this will also be Z. All of them are equal in terms of the real part as well as imaginary part. So this may have Z angle some phi, phase angle, and this will also be Z angle phi, and this is also going to be some Z angle phi. Okay, RL load I'm talking about. So I can connect this here, and I can connect this here, and I can connect this here. So if I look at the current here, this is going to be whatever is my V phase, right, divided by Z angle minus phi, right? Because V phase divided by Z phi. So when I take it on the top, I should say V phase divided by Z, because I could have connected this and this. Nobody can prevent me from connecting this and this, because I'm not going to have any current after all. All of them are going to be balanced. All three impedances are the same. So I will have the same current flowing through this. So I can call probably this as IA, which is equal to VA divided by Z angle minus phi. The same way I will have IB and IC. Okay. Now, if I say power delivered to one of the impedances, I should write whatever is V phase multiplied by I phase multiplied by cos of phi, because between this current and this voltage I am having basically a phase angle which is phi, because if I call this as Vm sine theta, I'm going to have this as Vm sine theta or omega t. If I may call this as Vm sine omega t, so I'm going to have this current as Vm sine omega t minus phi. That's what I'm going to get as the current. So divided by Z, sorry. That is going to be the current. Okay. So this is going to be the current value, small I. So if I'm calculating the power, I should write this as whatever is the per phase value, which will be Vm divided by root 2, and this will be Vm divided by root 2Z, that will be I phase, and cos phi. This is going to be power delivered to one of the impedances. So V phase, I phase, cos phi is going to be power delivered to one impedance. So power for all the three phases. If I try to write power for all the three phases, that will be 3 times V phase, I phase multiplied by cos phi. Please note the phase angle phi is only between this winding voltage and this winding current itself. Similarly, this winding voltage and this winding current. Similarly, this winding voltage and this winding current. Or if I am considering it from the load side, I should take it as one particular phase load and one particular phase current. That's what I have to look at, the load current and load voltage, the corresponding load phase voltage and the corresponding load phase current. I have to take the phase angle difference between these two as phi. This is what is phi. So I should be able to write this as 3 V phase, I phase, cos phi. So where phase, this is the phase angle difference between a particular phase voltage and the same phase current. So I cannot look at A phase voltage and B phase current and B phase voltage and C phase current. I'm looking at one particular phase voltage and the same phase current. Now, let me write this as root 3 times V phase and root 3 times I phase multiplied by cos phi. So I can say root 3 times V phase and root 3 times I phase and cos phi. I can do it like this. Now, if I am looking at star connection, I'm going to get root 3 times V phase as V line. And root 3 times I phase, I have to write this as root 3 times I line and cos phi. So I can write this as root 3 V line, I line, cos phi. So the power in all the three phases can be represented by root 3 VL, IL, cos phi. If I am looking at delta connection, I can write V phase is same as V line. So I can write root 3 V line. Doesn't matter. And root 3 times I phase I can write as I line. And I have cos phi. So whether I look at delta connection or star connection, the common expression for the power is going to be root 3 VL IL cos phi. So in general, I can write the three-phase power as root 3 VL IL cos phi as the overall power, three-phase power. If I am going to have all the three-phase voltages being balanced and the three-phase load also being balanced. What I mean by three-phase load being balanced is all three phases should have the same impedance with same phase angle connected. So if I'm talking about R plus JXL or R minus JXC, I should have the resistance values to be the same and the reactance values also to be the same in all the three phases. Only then I will say it is a balanced load. So this expression, which is the power expression, that is valid whenever I am talking about three-phase balanced supply voltage. What we mean by three-phase balanced supply voltage, the magnitudes of the voltage should be the same and phase angles should be shifted from each other by 120 degrees. And if I say three-phase balanced load, what we mean by balanced load is Z should be the same and phase angle, if I say Z angle phi should be the same in all three phases. Only then I can call it as, balanced load. So let me try to work out one small problem for a three-phase star connected 4-wire system. I'm going to work out one simple problem so that you understand what we mean by saying that the neutral current will be zero whenever we are going to have a balanced load and balanced supply. So I'm going to write the problem like this. 3 single phase loads of 1 kilowatt, 2 kilowatt and 3 kilowatt capacity at unity power factor. So cos phi is 1. Unity power factor are connected between the three phase lines and neutral respectively in A, B, C, in a three-phase system. I can say in a three-phase system. Calculate the neutral current if V line equal to 400 volts. So V line is 400 volts. That's what is given. And it is a star connected system. Okay. So obviously if it is connected between neutral, that means it should be a star connected system. It cannot be anything else. It cannot be delta. So if I want to do the solution, the first thing I can think of is, let us say I have 1, second and third. These are the three supplies. I can represent it like this, or I can represent it this way also. I can talk about this as VA. I can talk about this as VB, and I can talk about this as VC. These are the three phase voltages, and here is neutral. Okay. Now this is connected to a 1 kilowatt load. So this is going to be 1 kilowatt load, and this is connected between these two. Okay. If it is a bulb, I can show it like this, 1 kilowatt bulb. And similarly, I'm going to have another one. Maybe this is 2 kilowatt, which is connected between this line and the neutral. And I'm going to have from here also another one, which is 3 kilowatt. And that is going to be connected here. Okay. And what is being asked is, what is the neutral current between the neutral of the load and neutral of the source, IN equal to what? This is what is being asked. Okay. So I can say, first of all, IA will be equal to, if I say 1 kilowatt equal to VA IA cos phi. And after all, cos phi is going to be unity. That's what is given. This is unity. So I can write this as 1000 divided by whatever is VA magnitude. That I have to write. Similarly, IB has to be 2000 divided by VA magnitude, means that is V phase. And V phase, I can write that as 400 divided by root 3. So I can write this as 1000 divided by 230. And this is 2000 divided by 230. And IC is going to be 3000 divided by 230. Okay. So 1000 divided by 230 is going to be 4.35. And if it is a unity power factor load, I will have 0 degree phase angle. Whereas here, this is 2000 divided by 230, but it will have a phase angle of minus 120. Please remember. So this is going to be some, it will be twice this. So 8.7 angle minus 120 ampere. This will be minus 120 ampere with 8.7 as the magnitude. And this will be 3 times this. So I should have this as some 13 ampere or 13.04 angle plus 120. So the neutral current will be IA plus IB plus IC, which will be definitely not 0 because I have 4.35 angle 0 plus 8.7 angle minus 120 plus 13.04 angle plus 120. You can calculate this. Definitely this will not be 0, and that will be the current flowing as the neutral current between the source neutral and load neutral. Okay.